Okay, here we go. Kinesiology 230. And we are now into chapter 1, presentation 5. And we're going to go back a little bit and talk about actin and myosin and talk a little bit in terms of the actual muscle side of the equation and how the nervous system interacts with the muscle and kind of get a little bit more in depth here and just expand a little bit on our previous presentation. So our vocabulary refresher, we've already talked about epi, endo, and peri, mesium, muscle, sarco, flesh, mere, part or segments of sarcomere, right? Iso, aniso, and tropic. So similar, so isotropic would be similar and attracted to. Anisotropic would be different or dissimilar and attracted to. And we looked at this, and we looked at it in terms of down the myofibril, you have a sarcomere. The sarcomere itself is really where the contraction happens, and that happens between the actin and the myosin. That's seen in the muscle. The myosin here represented by this kind of, I don't know, maroon, kind of brown color. And this is more of a yellowish green color for the actin. And it's really a case where we've taken this down from, large belly of the muscle all the way down to this kind of microscopic myofilament actin and myosin, which is found here in the sarcomeres. And we talked a little bit in terms of this, in terms of having the Z's on each side, and then the Z's, everything happens in between them. And then within that, we have the I band, which is the orange, and we talked about that being thin, and you have thin being actin. And then from here, we have the I band, which is isotropic. We go into this next one, which you have the Z's on either side of the I band. And then from here, we go into, anisotropic. We have the A in the middle. Takes a step further, we have the thick lines in the middle, which are myosin. And the myosin are, when it's represented, you can see the whole thing a little bit better. You have the A band. Take this a step further, here's our myosin. You kind of see this even better yet. You have this in the middle. This middle was referred to as H, and this was H because when they probably looked under the microscope for the very first time, it came off as a little bit lighter, and they referred to it as heller or brighter region. And then we get into this line down the middle, the mittel, which is the M. All right, so we talked about all that, and then we jumped into this. We jumped into the neuromuscular junction, which is, the action potential travels along the motor neuron, represented up here. And then you have a release of an excitatory transmitter, acetylcholine, which is right here. And then acetylcholine is released into the synaptic cleft between the axon and the motor fiber. And that is then picked up by the acetylcholine. The receptors pick up the acetylcholine, which leads to an action potential along the sarcolemma of the muscle fiber. So again, it's a bit of a domino effect. Now I want you to think of this, just take a moment. If you and I are playing catch and you're just standing there and I throw you a baseball, you have to respond in fractions of a second, and just think of this process we just described that happens in fractions of a second, and not just with one muscle in my glove to catch the ball, but every single muscle in my body has to respond in a coordinated effort and have the motor neurons fire correctly and have the acetylcholine jump across the cleft correctly, and then be able to be picked up across the other side of the cleft and be able to lead to an action potential along the sarcolemma of the muscle fiber. Holy smokes, and that happens in fractions of a second. When you start to watch athletes in action, you really get a greater appreciation, man, of what those athletes can do. So you have this release of calcium, and this calcium from this process is released, and that release of calcium is picked up, and that's then what enables the interaction between the actin and the myosin. You need calcium in the process, denoted here in yellow, in the process to be able to allow an active site to happen between the myosin and the actin. And it's the myosin that has the cross bridge attachments on it, like the little oars that pull the active towards one another. So if we look at this and you go, okay, you have this diagram to the right, which we've seen 12 times already. You have the actin and the myosin, and it's within a sarcomere, and you have the calcium that enables the myosin to attract so that calcium allows this cross bridge attachment to happen to almost like an oar in the water to pull the actin. And then the actin is pulled like by a rowing motion towards the M line. So what happens is you have the M in the middle, and then you have the Z's on either side. When there's a contraction, you have the oars are facing one direction over here, the oars are facing the other direction over here. This is the midline, mitral, and this is your Z over here, your Zweichen. And what happens when this contracts is these little oars pull from left to right, these little oars pull from right to left, and the Z get closer to one another. It closes that gap between one side and the other. It's very much like two bookends just kind of coming together with every contraction. Pretty cool stuff, really is. So this is regarded as and widely accepted at this point until somebody proves it wrong or right. This is referred to as the sliding filament theory because you have the filaments of actin are being pulled closer to one another and they're sliding over the myosin because of the cross bridge attachment, and they're pulled towards the M line. And at this point, and at present, this is the best available explanation for this whole process. And quite frankly, it's one that really, I think, encapsulates a very complex process in a very simple kind of way.